students, and welcome to the lecture on statistical process control and process capability. After the lecture, we will be able to learn the following objectives. Explain a control chart. Discuss process capability. Explain process capability analysis. Describe control limits versus specification limits. Let's start with a brief introduction to statistical process control and process capability. Statistical process control is an analytical decision-making tool which allows you to see when a process is working correctly and when it is not. Variation is present in any process. Deciding when the variation is natural and when it needs correction is the key to quality control. The concept of statistical process control is based on a comparison of what is happening today with what happened previously. One can take a snapshot of how the process typically performs or build a model of how one thinks the process will perform and calculate control limits for the expected measurements of the output of the process. Variations due to assignable causes. Assignable causes of variation are present in most production processes. These causes of variability are also called special causes of variation. The sources of assignable variation can usually be identified, leading to their elimination. Chance variations or random variations. Random sampling seeks to select a truly representative sample of people from a broader population. A more formal definition of the idea is that everyone in the population has an equal and non-zero chance of being selected. Let's discuss the definition of control chart. Control charts are the basic tools of statistical process control. They are simple to construct and use, and are very useful at leading to process improvement in the language of statistical process control. How far can the process deviate from target and still be in control?
What is a control chart? What does it do for me? Why do I need one? Can't I just draw a plain old bar chart or something like that? And the answer is a control chart will help you find a lot of things that are going on in your process that you wouldn't be able to see otherwise. There's literally no way to progress from 3 sigma in the Six Sigma world to 4 sigma, 5 sigma, 6 sigma without a control chart. So how does this work? Well, let's say we're tracking something like errors. Well, it turns out we're going to plot the number of errors every day or every whatever, every period of time, and that'll create what's called a line chart. And it's also known as a time series chart because it shows the time of the flow of the process. Now, with the line chart, you can't really tell if anything's good or bad or stable or predictable. It's just a chart, all right? And so the first iteration of this was to change this to what's called a run chart. And we added an average line, and the average line here actually divides all this up. And so with all of that, we can start to see what's going on in our process, whether points above or below, and so on. And there are some ways to analyze runs in this type of chart and figure out if there's something unusual going on. But with the advent of modern software like the QI macros, it's unnecessary. We can just jump right over to a control chart. So a control chart begins, we start looking at the variation. So how far is each point from the center line? And if we take that bit of data, it turns into what's called the standard deviation. And that allows us to calculate an upper control limit and a lower control limit. And this type of chart would be known as a Levi-Jennings chart. There are other ways we can calculate variation. So for an XMR or X moving range chart, here you can see there's a difference between each point. And that's what we use as our variation. That helps us figure out how to create a control limit. In X bar R chart, we may be sampling 4 data points or 5 data points, and the range between those data points is what we use to start to figure out the variation and to calculate upper and lower control limits. Now, each control chart, once it's created, has 1, 2, and 3 standard deviation lines. The upper control limit is 3 sigma, and the lower control limit is minus 3 sigma. And that allows us to divide it up into zones here. So the first zone, called Zone C, has almost 2/3 of all of your data. The next zone up, Zone B, that includes 95.5% of your data. And the total outside would be 99.7% of all of your points should fall within the control limits. Now this enables us to do some analysis and figure out, is there something potentially out of control or out of whack with our process? So as you can see here, 99.7 means 997 points out of 1,000 should fall in here. Maybe only 3 points should fall outside of that control limit. Well, if you have something like you only have a dozen or more data points and you have 1 point outside that control limit, that's potentially an unstable condition. And this is one of the first rules that came out. These were developed at Western Electric in 1920. So you have to understand these have been around a while. There's no magic. This has all been tested. And once you have this out of control point, then we might want to come in and do some root cause analysis or special cause analysis. And we'd ask the 5 whys. Well, why was this point out of control? And that's what we want to do in each one of these types of conditions. Now, given that we have all these other lines, we can figure out some other potentially unstable conditions. So here you can see Zone B, we should have 95% of our data points in there. But if we have 2 out of 3 above 2 standard deviations or below 2 sigma, then that's 2/3 of your points, right? So 2/3 are outside. That seems to be out of whack with our 95% in this zone. Similarly, if we have 4 out of 5 points above 1 sigma or below 1 sigma, that's 80% of your points are outside of Zone C here. And 2/3 should be in here, so that seems like an out of whack kind of condition. We could also have 8 points above or below the center line. This is what's known as a run. One wouldn't expect there to be that many points above the center line. We can also see things like a trend, so 6 points descending or 6 points ascending are considered to be a trend. Another type of out of control condition is what's called hugging. If you have 15 points in a row right here in Zone C, well, guess what? We should have some points outside of here. So that means that for some reason the data is maybe being manipulated and needs to be investigated. So when you do have a stable control chart, as this one is, where there's just points and there's nothing out of control, then we can start to make improvements. All right, so we'd want to reduce the variation. So we want to take our variation and start to reduce and move the average line, in this case it's errors, and reduce the spread or the variation from the upper to the lower control limit. So that's our goal. That's what we want to create when we start making our improvement projects go forward.
Comparison of univariate and multivariate control data. Control charts are used routinely to monitor quality, depending on the number of process characteristics to be monitored. There are two types of control charts. The first, referred to as a univariate control chart. This is a graphical display chart of one quality characteristic. Characteristics of control charts. If a single quality characteristic has been measured or computed from a sample, the control chart shows the value of the quality characteristic versus the sample number or versus time. In general, the chart contains a center line that represents the mean value for the in-control process. Why control charts work? The control limits, as pictured in the graph, might be 0.001 probability limits. If so, and if chance causes alone were present, the probability of a point falling in the upper limit would be 1 out of 1,000. And similarly, a point falling in the lower limit would be 1 out of 1,000. Types of control chart. One has two main types of control charts, one for variable data and the other for attribute data. Since now the worldwide current operating level is number of parts defective per million parts produced, described as ppm, control charts for attribute data has no meaning. Following are the most commonly used variable control charts. To track the accuracy of the process, mean control chart or X-bar chart. To track the precision of the process, range control chart. Life beyond the mean and range chart. Statistical process control is based on a number of basic principles which apply to all processes, including batch and continuous processes of the type commonly found in the manufacture of bulk chemicals, pharmaceutical products, specialty chemicals, processed foods and metals. Control charts for variables. There is no readily available means for correcting, adjusting, or taking action on it. If the observed difference is known to be due to a special cause, then a search for and a possible correction of the cause is sensible. Adjustments by instruments. Computers, operators, instructions, etc. are often special causes of increased variation. Procedure for using variables control charts. Determine the variable to monitor. At predetermined even intervals, take samples of size n, usually n equals 4 or 5. Compute x and r, or s, for each sample, and plot them on their respective control charts. After collecting a sufficient number of samples, k, where k is greater than 20, compute the control limits for the charts. The following additional calculations will be necessary. If any points fall outside the control limits, conclude that the process is out of control and begin a search for an assignable special cause. When the special cause is identified, remove that point and return to step 4 to reevaluate the remaining points. If all the points are within limits, conclude that the process is in control and use the calculated limits for future monitoring of the process. Because the limits of the X chart are based on the variability of the process, one will first discuss the variability charts. If the R chart or S chart shows a lack of control, one cannot draw conclusions from the X chart. Did you know in 1990 the Gartner Group first employed the contraction ERP as an addition of material supplies planning, or MRP? The S chart. The S chart is used to monitor process variability when sample sizes are large, n to the 10th, or when a computer is available to automate the calculations. This chart is called the S chart because the statistic being plotted is the sample standard deviation. Using the S chart, we can see an estimate of the process standard deviation. The X chart. This chart is called the X chart because the statistic being plotted is the sample mean. The reason for taking a sample is because one is not always sure of the process distribution. By using the sample mean, one can invoke the central limit theorem to assume normality. Use of control charts. Control charts are used to investigate the variability of a process, and this is essential when assessing the capability of a process. Data are often plotted on a control chart in the hope that this may help to find the causes of problems. Charts are also used to monitor or control process performance. Effect of the sample size. The sample size has a major effect on the quality of statistical conclusions. This is reflected in the size of the confidence intervals for estimated distribution parameters, such as mean and standard deviation. Some control chart patterns. Statistical process control charts have been widely used for many years to monitor the quality characteristics of a process. A process is carried out of control if a point falls outside the control limits or a series of points exhibit an unnatural pattern, also known as non-random variation. Let's move to the next topic, which is process capability. A critical aspect of statistical quality control is evaluating the ability of a production process to meet or exceed preset specifications. This is called process capability. Process capability measures the goodness of a process. Comparing the voice of the process with the voice of the customer. The voice of the customer here is the specification range or tolerance and/or the nearest customer specification limit. Process capability is measured by the Process Capability Index. This is computed as the ratio of the specification width to the width of the process variability. Capability analysis is a set of calculations used to assess whether a system is statistically able to meet a set of specifications or requirements. To complete the calculations, a set of data is required, usually generated by a control chart. However, data can be collected specifically for this purpose. All methods of capability analysis require that the data is statistically stable, with no special causes of variation present. To assess whether the data is statistically stable, a control chart should be completed. If special causes exist, data from the system will be changing. Before capability analysis is completed, a histogram and control chart need to be completed. You can easily create these charts and perform capability analysis using software like Chart Runner, Lean SQC Pack. Capability analysis is a set of calculations used to assess whether a system is statistically able to meet a set of specifications or requirements. Measures of the process capability. Process capability indices. CP, CPL, CPU, and CPK are the four most common and time-tested measures of process capability. Process capability indices measure the degree to which process produces output that meets the customer specification. Process capability indices can be used effectively to summarize process capability information in a convenient unitless system. CP and CPK are quantitative expressions that personify the variability of processes, its natural limits, relative to its specification limits, customer requirements. Process Capability Index, or CP. Process Capability Index is a simple relative number comparing value of the required process variability, required tolerance interval, to a natural process variability, or natural tolerance level. Process Capability Index, or CPK. CPK reacts to deviation of the measurement process average, mean X, from check standard nominal value, XO. Did you know process capability is also defined as the capability of a process to meet its purpose as managed by an organization's management and process definition structures, ISO 15504. Process Capability Index, CPM. Practical experiences showed that demand for a low percentage of check standard measurements, or measurements performed directly on products or processes, falling outside the tolerance limit is not satisfactory. Little information is obtained on spare measurements. Now let's talk about control versus specification limits. Control limits versus specification limits are defined as: specifications are set up by the customer. These are the wishes. Control limits are obtained by applying statistical rules on the data generated by the process. These are the reality. Process capability refers to the ability of a process to meet the specifications set by the customer or designer. Process capability is based on the performance of individual products or services, not the subgroup averages, against specifications set by the customer or designer, not the statistically computed control limits. Process capability is different from the state of process control, which is determined by control charts and based on the average performances of subgroups against statistically computed control limits. Difference between process capability and the state of process control. When measurement of an individual item does not meet specification, the item is called defective. When subgroup averages are compared with control limits and the comparison shows some unpredictable amount of variation, an out-of-control state is assumed. A process in statistical control does not necessarily follow specifications. A capable process is not necessarily in control. Now in the end, let us summarize what we have learned in this lecture. Statistical process control is an analytical decision-making tool which allows us to see when a process is working correctly and when it is not. Variation is present in any process. Deciding when the variation is natural and when it needs correction is the key to quality control. Capability analysis is a set of calculations used to assess whether a system is statistically able to meet a set of specifications or requirements. Process capability indices measure the degree to which processes produce output that meets the customer's specification. Control charts are the basic tools of statistical process control. They are simple to construct and use and are very useful at leading to process improvement.